All right, I think we can slowly get going. So, hello everyone, and welcome to this new seminar of the Clever Planet for 2021 seminar series. I'm Maxime Maurice, a postdoc at Paris University, and along with Daman, who will take the floor in a few moments, we are your hosts today. And before Daman introduces today's speaker, I will give you a brief foreword about the Clever Planet project, which is an interdisciplinary multi-institutional research initiative to unravel the condition of planetary habitability in the solar system and beyond. The lead institution of the Clever Planet project is Rice University, and it is supported by NASA as well as one of the team of the Nexus Exoplanetary System Science Research Coordination Network under astrobiology. In this seminar series, we cover broad topics of planetary habitability that utilizes expertise in astrophysics, geochemistry, petrology, geodynamics, geophysics, and related disciplines. And before I leave the floor to Daman, I'd like to proceed to a land acknowledgement. And indeed, we think that we want to keep in mind that the research we are doing is done on the historical and traditional land of native people, and failing to acknowledge that is, in our opinion, perpetuation of the colonization. And here at Rice University, that means in the Houston area, we are the crossroads of several territories of native people. I'd like to first mention the Karankawa, who are now extinct, who went extinct by the mid-19th century, directly victim of the colonization. Then from the north of Mexico up to the Houston area is the traditional land of the Coahuiltecans, who are today represented by the Tapilam Coahuiltecan Nation. Along the coast of Gulf of Mexico, all the way to Louisiana, is the traditional land of the Ishak, also known as the Atacapa, today represented by the Ishak Atacapa Nation. And finally, the now extinct Sana, whose affiliation to a major group is not clear, but who have been still related to the Tonkawa via their language, the Tonkawa being today mostly settled in Oklahoma. And with that, I'll leave the floor to Daman, who will introduce our speaker for today.
Hi, everyone. My name is Damanvi Garewal, and I'm a graduate student at Rice University. Today, it's my great pleasure to introduce Professor Anders Johansen, a theoretical astrophysicist who did his PhD in astrophysics from Heidelberg University and Max Planck Institute of Astronomy, followed by his postdoctoral appointments at Max Planck Institute of Astronomy and Leiden University. He's previously been a professor at Lund University and now is a professor at University of Copenhagen. For his groundbreaking theoretical and computational work on the formation of planetesimals and growth of planetary systems, he has been awarded several honors, including Harold C. Urey Prize from the Division of Planetary Sciences of the American Astronomical Society, the Sten von Friesen Prize by Royal Physiographic Society of Lund, and Goran Gustafsson Prize by Swedish Royal Society. So just before giving the floor to Professor Johansen, I would like to specify that the format of the talk is 40 to 45 minutes of talk, followed by question answers of 10 minutes or so after the end of the talk. Question can be posted in the chat windows, and I'll narrate those questions after the end of the talk, or people or participants can raise their hands and I can unmute them at the end of the talk so they can ask their questions. So Professor Johansen, the floor is all yours.
Thank you, Daman. Thank you very much for this nice introduction. Let me get started with my talk. So first of all, I'd like to thank the organizers for inviting me here today to talk about my research. And the title of my seminar is Formation of Terrestrial Planets by Pebble Accretion. So I'll take you all the way from dust in protoplanetary disks over the growth of dust to form pebbles, and then how pebbles coalesce into planetesimals to continue to grow to real planets. And particularly this part is important here, terrestrial planets. that is only in the last year or so that I started working on the formation of terrestrial planets like Earth by Pebble Accretion. And I believe I can present here today some compelling evidence that actually the Earth formed in a very different way from what we normally think. Okay, but let me get started, and we can start by looking out into our galaxy, and then we can look at young stars and we can find out where planets form today. And planets form in these protoplanetary disks of gas and dust that you see here. What we're seeing here are actually images made with the ALMA telescopes by the so-called D-sharp survey. And what we're seeing here at millimeter wavelengths is not the so much emission from the star. We are seeing the thermal emission from disks of gas and dust that are orbiting around these stars. So the gas and dust have been heated by the stellar light, and then it's been reprocessed into longer wavelengths, which we're seeing here. These disks have typical sizes of 100 astronomical units, so very similar to the shape or to the scale of our own solar system. And they contain probably 99% gas, helium, and hydrogen, which is impossible to see at these temperatures, or at least very, very hard. And then 1% dust and ice. And dust and ice carry the main opacity here. So what we're seeing here is therefore the thermal emission from dust and ice pebbles around young stars. They have typical disk masses between 1% and 10% times the mass of the star, so there's plenty of material there to build planets from. Now, these are snapshots. We can also do statistical surveys of the dust mass for different evolution stages of the star. And here's a class 0 and a class 1 and a class 2. Class 0, class 1, and class 2 stars. And sort of, we should think of class 0 and class 1 stars as being maybe less than 1 million years old, and class 2 stars as being a few million years old. This plot here shows the cumulative distribution of dust mass in logarithmic units here. So 1 Earth mass, 10 Earth masses, 100, 1,000 Earth masses of dust, and this is the cumulative distribution. So we see that with time, the mean amount of dust, if you do the 50% line here, with time that amount is actually falling. So we start out at the class 0 state, very young stars, to having several hundred Earth masses of dust and ice, and then it drops steadily over 1 million years down to maybe 100, and after a few million years, there's only some sort of like 10 Earth masses of dust left. So this tells us that protoplanets disks live typically for 2 to 3 million years. That's probably mainly because the gas and dust are accreted onto the star. Some of the gas is photoevaporated, some of the dust goes into planets, but the main process is probably simply transport onto the star. And therefore, dust must grow rapidly to form planets before the disk is emptied onto the star. So now we have a pretty good timescale constraint on the timescale over which we need to form planets. Right. So the first step of planet formation is then that we start with the micrometer-sized dust grains that form in outflows from ADP stars and supernovae and so on. They enter this protoplanetary disk, and then they come into such a dense environment that they start to coagulate very frequently, and then they stick when they collide with each other. So people have done experiments in the lab showing that micrometer-sized dust grains actually stick really well when they collide. Lots of people have worked on the coagulation of dust in protoplanetary disks. I'm just showing here a paper from my own PhD student, Lynn Eriksson, that she published last year, which shows a global calculation of dust coagulation in protoplanetary disks. So we start here sort of at 8 astronomical units, all the way out to several hundred astronomical units. If you just focus on the top plot here, we started all our dust here at micrometer size, so down here. And already after 50,000 years, that's the blue one, then dust within 30, 40 AU has coagulated up to become millimeter in size. It goes really fast. It takes a little bit longer time in this region here, as you can see outside, because the density is lower. Then it takes maybe a few 100,000 years before that also reaches millimeter sizes. But it's still short compared to millions of years, which is the lifetime of the protoplanetary disk, right? So why doesn't it grow anymore? That's mainly because at some point the particles become so large that they start to collide fast. They could become compact, very compact little millimeter, centimeter sized dust particles. And compact particles don't stick well when they collide. They will bounce off each other. They will fragment each other. So there's a good physical reason for why this doesn't grow to more than millimeter sizes. So this is fine. This can explain our ALMA images of protoplanetary disks that have lots of emission from apparently millimeter-sized dust. But if you want to go on and form planets, coagulation is not a good way to continue. It simply doesn't work well beyond this size. There's an additional problem here. That is actually that these pebbles in the disk that are formed, they're also drifting fast towards the star. So with time, the pebbles in the disk are being emptied onto the star. That's sort of part of the accretion process that I told you about. But if we want to go now from pebbles to the next growth stage, which is planetesimals, they're sort of like asteroid-like bodies, then we need to get the help from gravity. We need to help not the gravity from two individual pebbles because it's too tiny. They don't fit each other. We need the gravity from collective groups of pebbles to come together and then contract under their own weight, much in the same way as you need hydrogen to come together to form stars. Yeah. So the gravitational attraction between two pebbles is tiny. So what can we do? Well, it turns out that if you put pebbles and gas into a computer simulation, then they will spontaneously form very, very dense clumps. And this is a mechanism called the streaming instability that I have worked on ever since my PhD time, almost 15 years ago now. And the essence of the streaming instability is the following. We start with micrometer-sized dust grains, like this interplanetary dust particle here. And then these dust particles collide and stick together, and they will form something like these guys here. So millimeter to centimeter sized dust aggregates, but these are not igneous rocks like you find down at the beach. These are made out of micrometer sized dust. And if you take such an aggregate here between two fingers and you squash it a little bit, then it's going to polarize again. They are very, 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 very fragile. That's one of the reasons why you cannot really grow them much more. Now, the essence of this streaming instability mechanism is illustrated here. If I take a pebble here in a protoplanetary disk, then as it orbits around the star, it will encounter the gas that's orbiting a little bit more slowly than the pebbles are. So the gas is orbiting a little bit more slowly than the Keplerian speed. The reason is that the gas, if the gas would only feel gravity, so you should imagine that the star is in this direction somewhere. If the gas would only feel gravity, then it would orbit at the Keplerian speed, just like a planet. But there's an additional force that this protoplanetary disk is hotter and denser on the inside and colder and less dense on the outside. So there's a pressure gradient that pushes out on the gas. And this acts like a slight reduction of the gravity. And therefore the gas is moving what we call sub-Keplerian, a little bit more slowly than the Keplerian speed. I'm showing that with downward pointing arrows here. We're in a co-rotating frame here. So the pebble here would like to orbit at the Keplerian speed, but it gets the headwind from the gas, and therefore it spirals in towards the star. But the essence of the streaming instability is that if you can concentrate a pebble slowly in a filament here that's a little bit more dense than the surroundings, then these pebbles can locally force the gas to move closer to the Keplerian speed because now the pebbles are dominating the dynamics and they don't feel this pressure gradient. When the Keplerian speed is, when the sub-Keplerian speed becomes closer to the Keplerian speed, as we're seeing here with shorter arrows, then the headwind is shorter, then the radial drift speed becomes lower. And there you can see that we're driving a runaway process now, whereby we are adding drifting pebbles into this filament. That's adding to the mass of the filament. That makes the filament able to even more dominate the dynamics and accelerate the gas to move at the Keplerian speed. Then the headwind goes down, and then you're even more able to catch drifting pebbles. So it is a linear instability, and if you put it into a computer simulation, it looks something like this. Here's the filament. It formed completely spontaneously. There's no, it's formed even without gravity. At some point, gravity takes over, and that's actually what you see here, that it becomes very thin in certain places. That's because once the filament becomes thin enough, then the gravity pulls it together even more. And at some point, the local density becomes so high that the gravity can win over the tidal forces of the star, and then simply regions can contract to form planetesimals. These planetesimals have sizes from 10 kilometers to several hundred kilometers. Just showing a few arrows here on some dots, which you see here. So the typical planetesimal we form is 100 kilometers in size, sort of similar to a typical asteroid in the asteroid belt. So we think this is a good explanation for the characteristic size of asteroids. Some are smaller, maybe down to 10 kilometers. That's more like a comet size. So the comets will be dominated by a number by the smaller sizes. So that's maybe why we have so many small comets and not so many large ones. And finally, some of them actually become binary. Maybe I can zoom in a little bit here. Yeah. You can see here it's very cute. Here are actually two planetesimals orbiting around each other. This is a planetesimal binary. When we go to higher and higher resolution, we get more and more planetesimal binaries out. And this is important. I will come back to that because we observe many binary planetesimals in the Kuiper belt beyond Neptune. Yes, I just wanted to make the point that the streaming instability is a process that's studied by many groups now, and people are adding various effects to it, including the effect of having a size distribution of particles and so on. But it seems like a very promising way to make planetesimals. Okay, we can now do statistics again, and then we can make big box simulations, and we can form a number of planetesimals with streaming instability, and then we can try to measure the initial mass function. Just like we like to talk about the initial mass function for stars, we can have an initial mass function for planetesimals also. So the characteristic size of planetesimals is about 100 kilometers, but actually, and then it looks like 100 kilometers would be somewhere around here, I guess. And then it's going to look like a power law towards smaller sizes, and then towards larger sizes, it looks like there's an exponential cutoff. Yeah, so it doesn't continue forever, that power law, there's an exponential cutoff there. And the power law exponent is somewhere in the range 1.5 to 1.7 when you write the IMF as dm going as the power law m2 minus alpha. That's sort of what we are starting to see here for low masses. And then for high masses, you make an exponential cutoff. Then you get a power law sort of around 1.6 or something, and then you get this beta parameter here. The exponential cutoff to be actually very mild. It actually means that beta is so low. It actually means that even though you form characteristic planetesimals with a size of 100 kilometers, you're probably going to form a few that are 600-800 kilometers in the size. And that's going to matter a lot actually for the subsequent planet growth process. This is a simulation here done by Simon et al. 2017, where they show 4 different particle sizes. So the blue one is roughly meter-sized pebbles, so kind of boulders. The black one is sort of 10 centimeter sized, and the red one is sort of down to centimeter sizes. And you sort of see the same power law emerging for all of these sizes of pebbles. So it seems that this power law here is rather independent of the size of the pebbles. All right. So we can go out to the Kuiper belt. The asteroid belt is fun to study, but asteroids are unfortunately very collisionally evolved. The asteroid belt is not in its primordial state anymore. If you want to find primordial planetesimals to compare theory to, then you have to move to the outer solar system, to the Kuiper belt. So NASA's New Horizons spacecraft flew past the Kuiper belt object now called Arrokoth in January 2019, and it turned out famously to be a contact binary, beautiful binary planetesimal where the two objects are actually touching each other, but with a nearly spherical shape of both of these components. So a year later, the New Horizons team published 3 papers in Science where they tried to find out how could this object have formed. And one thing they tried was to collide 2 separate lobes with different speeds. Here's a collision with 10 meters per second. You can see it's a complete catastrophe. It doesn't look at all like what we're observing. Even 5 meters per second is too fast, apparently, because this neck region is destroyed. You have to go down to 3 meters per second or slower before these 2 components can collide at a speed where they maintain their shape afterwards. So this is a clear indication, actually, that this object did not form as 2 separately formed planetesimals collided. It must somehow have come together very, very gently. And this, they say, support for the gentle accumulation model, which is sort of the streaming instability, that everything is forming in a very gentle way rather than the violent collisions. And the idea is that this used to be a binary, then for some reason, maybe gas drag, the 2 components came together and collided sort of at their mutual escape speed, which is sort of around 3 meters per second. There was another nice result for the New Horizons mission, and that is that the impactors, the craters on Pluto and Charon, actually fits kind of nicely the initial mass functions that we see here from the 2 different groups. So even though you can't observe small Kuiper belt object that well, by studying the surfaces of Pluto and Charon and also Arrokoth, you can count the number of craters, and you can say something about what the mass function is of planetesimal today. And then since we're in the Kuiper belt, that's probably similar to the initial mass function, but that looks a lot like the streaming instability simulations also. Yeah, so a little bit more about binaries, because there are many binaries in the Kuiper belt that you can observe from the ground, and it's a matter of getting good statistics on that. And that was sort of getting there a couple of years ago in this big survey by Grundy 2019. And one of the statistics you want to have is whether the binary in a pair, whether if this is the sun, whether they orbit around each other in the same direction as they orbit the sun. That's prograde. That's like the Earth orbit around the sun. Or if they go the other way around, that will be retrograde, or they can be spinning on the side. And that tells you something about how these objects form. So this Grundy survey here have now a lot of the binary Kuiper belt objects in it. And this is a plot of the mutual separation between the two components, where one is the maximum, and that's the Hill radius. And you can see this, so that's the separation. And then the other axis here is the obliquity, where 0 to 90 degrees is prograde. That means that the angular velocity vector points up, and 90 to 180 degrees is retrograde. And you can see here that there's a clear preference for prograde orbits of these binaries. And that's actually very important, because if binaries would form by three-body gravitational processes, where three objects come close to each other and then one leaves with a lot of energy and the two others are spinning around each other, then there will be a weak preference for retrograde. But there's clearly a very strong preference for prograde here. So Ms. Volatiles in 2019 made a nice cover of Nature Astronomy here by actually going into some of their computer simulations of the streaming instability and measuring the direction of rotation of all these clumps. And then they could do some statistics on it. That's what we're seeing here. This is the inclination. 0 to 90 is prograde, 90 to 180 is retrograde. And we see here that, let's see, so the black line here are the simulations, a clear preference for prograde, sort of 80% prograde, 20% retrograde. And the dashed lines here are the observations. They look very, 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 very similar. And this is another indication that planetesimals in the Kuiper belt formed in a process involving dust clouds coming together under gravity to form planetesimals, and probably in a process that is related to or is exactly the streaming instability. And the idea with our friend Arrokoth here is then that it used to be two orbiting around each other. Maybe gas drag made the two components spiral in towards each other, and then they could collide at a very slow speed. All right, that was something about planetesimal accretion, but we can actually have our planetesimal formation, but we can actually continue on and say, well, how are we going to form planets out of those? How do the largest planetesimals now continue to form planets? Traditionally, it's been thought that planets formed by planetesimals colliding over a long time and then forming both the cores of the gas giants and also forming the terrestrial planets and the super Earth and so on. But there's a problem in that theory, and that is that it's really inefficient. So actually planet growth by planetesimal accretion is very inefficient. I will show that more on the next slide. Actually, it's much more efficient to accrete pebbles, and that may be a little bit surprising, because why would you prefer a small pebble over a large planetesimal? Well, it's because if you are a planet here that is growing, and this is your Hill radius, so that marks the region over which you can scatter incoming planetesimals and pebbles, then typically a planetesimal which comes in does simply get scattered. It's just an energy and angular momentum conservation, that it comes in, it gets scattered, it goes on a more eccentric orbit. It's very unlikely that this planetesimal will actually hit onto the surface of that planet. Replace the planetesimal by a pebble, and they will initially follow the same trajectory, but then the pebble is feeling so much friction from the gas that it's losing kinetic energy. And as it does that, it goes from being in an unbound state out here, where the energy is positive, and as it's losing kinetic energy, at some point it gets a negative energy relative to the protoplanet growing in the middle. And then it's bound, and it's still losing energy, and then it has no choice but to spiral in and collide with the protoplanet. And this way, Pebble accretion can be much more efficient than planetesimal accretion. And of course, the mass of the bodies doesn't matter for the total accretion rate, because for each planetesimal, there will be zillions and zillions of pebbles, right? So it is much more efficient. So one can then make these kind of tracks here, where we can start by trying to make giant planets. So we can start far out in the disk, maybe at 20-30 AU. And then we can let the planets grow by Pebble accretion. That's the blue line here, that's the core growing. And then when they reach around 10 Earth masses, then they start to accrete gas and become gas giants. That's the orange and the red lines here. And you can see at some point they start to migrate towards the star also. And they sort of land after a few million years in the right regime of being Saturn to Jupiter mass and being at a few AU. So this is a good way to form planets, giant planets. If you go closer to the star, then we form something else. Then we start to form super Earth. Here, the outermost line here is when you form early on, and then it's later and later and later. The reason it says H2O here is this is approximately the location of the water ice line, where water vapor becomes in icy form. And then ice line moves in with time. So if you start early, we can form something like a hot Jupiter here, which is going to grow up to 10 Earth masses, and then we go in and become a hot Jupiter. If we start a bit later, a little bit further in, then the core starts to grow at a few Earth masses, and then it cannot really accrete much gas, and it ends up something like more like a super Earth. So this is sort of an overview of what Pebble accretion can do. But let's go back to look at the problem with planetesimal accretion, the traditional model. And the problem with planetesimal accretion is that it's quite efficient inside of a few AU, but outside of a few AU, it gets very, very inefficient. And then it's very hard to make it consistent with the migration of planets. So this is a paper that we published in 2019. It is this paper here, Johansen and Bits 2019, where we wanted to really see, can we really do this with planetesimal accretion also? And it turns out that it's very, very hard. Here we actually go to our most generous model that we make 1,000 Earth masses of planetesimals. That's a lot. And we put it into a protoplanetary disk, and then we start planets growing in different places, and we let them grow by accreting planetesimals, and we let them migrate. And then we can see, if you start at 5 AU, we can sort of grow something up to 10 Earth masses and then accrete gas. But while they do that, they also migrate and become sort of hot Jupiters and warm Jupiters. If we want to match anything like Jupiter and Saturn, we need to start further out, but then you see the growth is so slow that basically nothing happens. And it gets completely hopeless with Neptune and with Uranus and Neptune. So it is really, and this is with 1,000 Earth masses of planetesimals, is not even enough to form the solar system. It doesn't really help to go to smaller planetesimals. That's the red line here. It grows a little bit more efficiently. We decrease the migration also, and that doesn't help. That's the yellow line here. So it's really, really, really very, very hard to form planets by the traditional planetesimal accretion. We can obtain it if we have almost no turbulence, so that the planetesimals have a very low scale height. And also with very small planetesimals, that we can sort of form Jupiter, but it gets impossible for Saturn still. This was not so, maybe not so surprising, because it basically confirms in-body results that have been done in the past by Thomas et al., Levison et al., Coleman and Nelson, that basically planetesimal accretion cannot explain the architecture of the solar system, I would claim. Okay, but what about Pebble accretion? So Pebble accretion can make this nice growth track where Jupiter starts far from the star and it grows and it migrates in. But do we find any evidence that this happened in the solar system? And we think we actually do, and that comes from a little bit of a surprising side, namely in the Jupiter Trojans. So Jupiter is here, and here's Mars, and in between Mars and Jupiter we have the asteroid belt. But there are also the two Trojan populations that are caught in Lagrange points ahead and behind Jupiter. And the mystery here is that Jupiter's leading Trojans, those that orbit ahead of Jupiter, are 1.6 times more populated than the trailing population. And this is completely unexplained. It really shouldn't be that way at all. They should be captured equally well in both. But what happens now if we take Jupiter and we let it form in the sort of 10 to 30 AU region, and then we can let it migrate in and catch the Trojans on the way, and then we can see what basically happens. So let me go and look at this one first. So we sort of had different growth tracks here, where we start Jupiter at 6 AU all the way out to 30 AU, and then would Jupiter grow and migrate into its current position. Here's just one example of what these simulations look like. In-body simulation, lots of planetesimals here we put in the 4 giant planets growing and migrating in. And then we can see that as the Jupiter migrates in and Saturn migrates after, you get complete chaos. The planetesimals are like everywhere. After a while, a lot of them are ejected from the system, and some are scattered to the Oort cloud and so on. And then we are left with sort of a Kuiper belt, some stuff in the asteroid belt here. And then you see both Jupiter and Saturn have captured Trojans here. And when we measure then how many are in front and how many are in the back of Jupiter, we find, and bear with me here, this is for different, let me just zoom in. This is for different migration rates of Jupiter. In situ, Jupiter forms at 5 AU, and out here times 2 means that Jupiter forms at something like 30 AU, so delta A 26.9 AU. See, when we form Jupiter in situ, the asymmetry ratio between the leading and the trailing Trojans is 1, so it's the same number in both components. And as Jupiter is allowed to migrate over longer distances, then actually we get this asymmetry here. And it has to do with when Jupiter is migrating in and is capturing these Trojans, then because of the movement of Jupiter, then the stability regions in front and behind are changing shape a little bit. People have derived that from celestial mechanics, and they change shape in such a way that it's the leading Trojans that become more easy to capture than the trailing Trojans. So Trojans are captured asymmetrically in agreement with observations. Jupiter's Trojans are the same color as Neptune's Trojans. That's very exciting also. So maybe they formed in the same place. So we believe that the Trojan asymmetry may be the first evidence actually that Jupiter's core grew most of its mass far from the sun. Yeah, and not at 5 AU, but at least at 10 AU and preferably further away from the sun, because it has to have the same Trojans as Neptune basically. And we think Neptune formed in the 20-30 AU region. All right. So now that I hope I made the argument that Pebble accretion is crucial to form giant planets, then we can also ask ourselves, well, if we need all these pebbles to form giant planets, those that are not captured by the giant planets are going to rush through the inner solar system, and there's going to be pebbles drifting through the disk at a rate of about 100 Earth masses per megayear. The inner solar system is going to see a lot of pebbles drifting by. So surely Pebble accretion must matter also for super Earth formation and maybe even for terrestrial planets. So we have so we basically have here a simulation presented in Lambrecht et al. 2019. There's an in-body simulation that includes embryos that can collide with each other and also Pebble accretion. And you see here, when we start our embryos here between 0.5 and 3 AU, and we have to be sort of moon mass, then if we have a very low pebble flux, then these embryos are growing by Pebble accretion, and they're drifting in a little bit, and then they sort of get stuck at point a few Earth masses. Then after 3 million years, we have this population here. You run it for 100 million years, and you recover what I would call classical terrestrial planet formation. That is by mutual giant impacts here, you form some planets that are sort of Earth and Venus and Mars-like. However, if you add a little bit more pebble flux here and add a little bit more, so that the protoplanets grow faster, then they become more massive, they migrate more, they start to collide with each other. That's why some of these lines are missing. And then at the end, you get a population of objects that are maybe between 1 and 10 Earth masses. And they will also collide with each other in a hypergiant impacts and will actually form super Earth chains, so to say. Yeah. So a high pebble flux leads to the formation of super Earth systems, and a lower pebble flux leads to the formation only of these kind of embryos. And this means that the formation of super Earth and terrestrial planets are actually connected processes. They are connected through the value of this pebble flux here. Then there is an issue that has been brought up about these kind of theories that super Earth form in the disk and then migrate, and that is that super Earths then go into resonant chains. That's basically what we're seeing here of these results. If we look at the blue and the orange line here, we see after 3 million years, so to say, where the system has formed, you see the cumulative fraction, and this is the period ratio. And we see that a lot of these systems are actually caught in various mean motion resonances, 5 to 4, 4 to 3, 3 to 2. This is observed sometimes in exoplanet systems, but not always. And there is then the point that we need an additional phase where these kind of resonant chains, they go unstable, start to interact with each other, and there are massive collisions between planets, and some are colliding with the star. And then actually, in the end, when you run for a few 100 million years, then you can see we break all these chains. The separation is spread out to much higher period ratio for these two simulations here, with a nominal flux and a higher flux. And we can see that they start to look a lot like the data from the Kepler satellite here. So that even if things are initially in resonances, then these resonances are easily broken. And that's something that Isidoro has worked extensively on also. Okay, but let's move on to sort of the last third of my talk, where I will go and actually claim that even the Earth and terrestrial planets formed by Pebble accretion, because I showed you here something with moon mass embryos and super Earth forming, but there's also an in between where you can actually stop at terrestrial planet masses. So one thing I've always been excited about is that when you look at Venus and Earth and Mars in this way here, it sort of looks like two large planets and then one small planet. That looks a lot to me like a growth track from Pebble accretion. If planetesimals form at 1.6 AU, grow there and then migrate out, then you will naturally have the two large planets on the inside and Mars, the small planet, on the outside. So actually, one can now make a simple Pebble accretion model with some pretty low pebble flux and reasonable pebble sizes, and then you can find these black tracks here, which are actually calculations of growth and migration. And you see how Venus and Mars can lie pretty well on the same track, actually, so that Mars is just a sort of a latecomer in the game. And then the Earth is here. The Earth is a little bit too high. Earth should be less massive than Venus in this picture. But then our view is that there was a fifth terrestrial planet forming here, if you wish, Theia, of 0.4 Earth masses that collided with the proto-Earth to make Earth a little bit larger. So Earth would have been smaller if it hadn't had a giant impact. Yeah, so we must form an additional planet Theia that collides with the Earth later to form the moon. So actually this is nice, because when Earth and Theia grow from the same pebbles that are drifting in, then they naturally get the same composition. And this could maybe explain why the moon has a similar composition to the Earth. So this is how it goes when you form terrestrial planets by rapid Pebble accretion. This is the mass, this is time. And we can see here we have to start the planets sort of growing within a few million years, and then they are growing up at a rate of about 5 mega years to grow up to 1 Earth mass. And we start Venus first to get the innermost one, then Earth and Theia we start a little bit later, then we later collide, and then we start Mars even later to become smaller, basically. So that's how we form a smaller Mars. We can also do a more statistical approach to this. Then we can start a number of points here around 1.6 AU, a number of black points at different times in our evolving disk. And you can sort of see the statistical outcome here is a pretty good match to Mars, Earth, and Venus here for a pretty low pebble flux. And if we go and have a little bit higher pebble flux, then we can see that we overshoot and we get more like super Earth again, just like I showed from the Lambrecht L2019 paper. We can also make a broader distribution of planetesimals from the beginning between 0.5 and 1.5 AU or 2 AU, and then everything turns into planets and we don't have any characteristic planet mass anymore. So we think this kind of compelling evidence that maybe there was a very early planetesimal formation built out here at 1.5, 1.6, 1.7 AU, from which all the terrestrial planets grew and then migrated in. Right, but I want to continue a little bit and talk about some work I've been doing in the past year or so on the composition of planets that grow by rapid Pebble accretion, and particularly then that volatiles such as carbon and water is not delivered by giant impact, but actually delivered by what I call pebble snow, or what Ida called pebble snow in 2019. Which are basically pebbles raining down on this growing planet and carrying along with them volatiles. And one very important thing about that is that as the pebbles are going towards the growing protoplanet, then there will be a hot envelope that they have to pass through. And that hot envelope can actually thermally process these pebbles, and that can remove some of these volatiles again. So basically what I'm showing you here is the surface temperature of a planet that's growing as a function of its mass. And initially the planet is cold. We're now outside of the water ice line that is 120 Kelvin, and the planet grows with a full inventory of ice and organic carbon and organic nitrogen and a lot of things. But then at some point, if we will continue this game, we would fill the Earth up and be 30% water and 1,000 ppm nitrogen, and it would be way, way too much. But luckily, at some point around 0.01, 0.02 Earth masses, the envelope starts to become so hot that, for example, I'm looking at water here, that the sublimation temperature of water is like 170 Kelvin. When the surface temperature goes above that temperature, then as a pebble comes down to the surface, the ice is sublimated off as vapor, and this vapor is then transported back to the protoplanetary disk. Yeah. And I'm plotting here also the so-called radiated convective boundary here in this case, which is at temperatures above that is the interior of the envelope. Then the atmosphere is bound and not coupled to the protoplanetary disk. So if the ice line would move to above, or rather if the temperature of this boundary would be below the water ice line, then the water vapor would be trapped in the atmosphere, which would probably happen at 10 or 20 AU, but not around 1, 2, 3 AU. So we think this is a good way to explain why a planet like Earth has so little carbon and has so little water. So this is what I'm showing here in our simulations as a function of the growth of the planet. This is the water fraction of the planet for 2 different assumptions about water, and this is the carbon fraction. So the water fraction initially goes up and up and up. It's cold, it's accreting icy pebbles, they have 30% water with them, and it goes up to almost 10%, which is of course much more than we have on Earth. But then when we reach this 0.02 Earth masses or something, then it gets too hot to accrete water. And then from there on, we get cold, we get dry accretion, and the water fraction drops down to basically a few thousand ppm, which is sort of similar to what is observed for Earth. We could do a similar trick with carbon. Basically, we can accrete very carbon-rich material early on and get maybe several thousand ppm of carbon is what I'm showing you here. We need to go down to 500 or 1,000 maybe to match Earth. But then carbon is typically sitting in organic molecules, and they also tend to get destroyed in a similar way as water sublimates. These organic molecules are destroyed typically at 200, 300, 400 Kelvin. So that's what we're seeing here also, that the carbon is dropping down. So Pebble accretion gives a pretty good match both to the water and to the carbon of Earth. Right. So we can now take our planets that are growing by Pebble accretion, and then what I've done is that I've developed a code that I call ADAP. Yeah, doesn't matter what the acronym is. And this is, I have just submitted 3 papers actually on the results of this ADAP code. And what we have here is that we have a planet formation model that grows a planet and migrates it, and then we couple it with an interior structure model. So it's a 1D interior structure model. And then I'm following what happens to the interior of the planet, what happens to the surface of the planet, and what happens to the atmosphere of the planet. So the first thing to notice here is just what happens here with time. So early on, when we have a small body, actually, so here we're around still at like asteroid mass or maybe a little bit higher. Then it melts by aluminum 26, and it forms a water ocean early on. And it also, a lot of the water goes into clays. That's sort of the yellow material here is basically clay. Then as we are growing more and more, then we are actually forming an early core. There's a core, this is a mantle, this is aluminum 26 that has formed sort of early core, but we're still not very massive. It's still basically a planetesimal. So when aluminum 26 runs out after a few million years, then we accrete more and more water-rich material here, which is heated enough to have a water ocean, and some of the water goes into the clay, but not much else happens beyond that. But then at some point it gets so hot at the surface that the planet differentiates basically, and then we get a fully differentiated planet here with a magma ocean here, and also with the metal core. I can show you here the surface temperature as a function of time for our Earth analog. So we go on this axis here, we can see that it's just a few hundred Kelvin. And at some point, the surface temperature shoots up to several thousand Kelvin. That has to do with the temperature by which the runaway greenhouse effect sets in, that it's accreting so much that it gets a runaway greenhouse effect, that and it has a very massive atmosphere, so that the surface is heated to several thousand Kelvin. And then the planet differentiates from the surface and down. Basically, when the first layers melt to form a magma ocean, then the metal separates from the silicate. The metals fall down, release energy that melts even more, and then you get a runaway differentiation. So this way, in the Pebble accretion models, planets naturally get magma oceans simply because they have these immense accretion rates. Whereas in the traditional picture of planet formation, you need giant impact to make magma ocean, which is a little bit more stochastic. Right. Let me move on a little bit. So can someone say how many minutes I've left? 5 or something? Or
you're almost like 5 or 10 minutes, maybe 5 minutes or something.
Okay. No, I should be able to finish in 5-10 minutes. I just want to show you actually that we think that the dating of the formation of the Earth is consistent with Pebble accretion. And the way that the Earth formation is normally dated is by hafnium tungsten dating, which basically is the effect that 182 hafnium decays to 182 tungsten with a half-life of about 9 mega years. Then as the planet separates into a core and a mantle, then the tungsten goes into the core and the hafnium remains in the mantle. And then the idea is that depending on when the hafnium is left alone in the mantle, if it's while it's still active, hafnium 182, then there will be an ingrowth of tungsten 182 in the mantle. Whereas if the differentiation happens late, then there's no hafnium 182 left basically, and then there will be no tungsten 182 in the mantle. So the more tungsten 182 in the mantle, the earlier the core formation. By definition, we measure this hafnium, this tungsten excess in a way by which the Earth has exactly 0. The chondrites have -2. That's sort of the value you would have if you would not have any local excess of hafnium ever. And actually, if you form the Earth core very early, then the Earth should have had a very high value of this epsilon. Basically, there should have been a lot of ingrowth of tungsten 182 in the mantle of the Earth. Let me show you that here. Here we have our model from the Pebble Accretion that we grow Earth up to only 0.6 Earth masses within 5 million years. Then we wait 40 million years. Then we make a giant impact that grows it all the way up to 1 million years. If you then measure this this tungsten 182 excess, then you can see since the Earth formed so quickly, then there's an enormous excess tungsten 182 up in the Earth mantle, which we don't observe at all. It should be 0. But then look what happens when the giant impact comes. If the giant impact is giant enough, then the core of the impactor can bring so much tungsten 183 and 184 into it that this excess is completely erased and can actually drive it down to be 0. Yeah. So early core formation implies very high values of epsilon W. The moon forming impact can reduce to epsilon W equals 0 if the impact is massive. So rapid Earth formation is actually consistent with the hafnium tungsten dating. That's something I was quite surprised to find, but it's sort of been seen in the literature also, something about you and Jacobson, who said the Earth maybe formed in 10 million years, whereas here we will even say it formed in 5 million years. Yeah, one can sort of put a little bit more quantity on this and say what kind of models are consistent with this low value of the tungsten excess for Earth. So basically, I'm showing here as a function of the mass of the impactor and the time of the giant impact, what becomes the tungsten 182 excess. And you want to read 0. That's what I'm seeing here. So in this case here, when there's complete equilibration between the core of the impactor and the mantle of the Earth, we can sort of either have 0.5 Earth mass impactor early, or if you go to lower and lower masses, it has to happen later and later. It has to happen later and later. So in principle, it could happen very late if you fine tune it to be 0.3 Earth masses. That's if you have complete mixing between the core and the mantle. If you have less, if you only have 50% mixing, that some of the iron from the impactor core doesn't interact with the mantle of the Earth, it goes directly to form the new core, then you actually need to have a really massive impactor. Then you need something like between 0.45 and 0.5 Earth masses, so almost equal sized impactors. Yeah. But you see here, in both cases, we put the planet accretion timescale to be 5 million years. So I would say that a planet accretion timescale of 5 million years, which we see in the Pebble accretion model, actually favors a massive impactor at least 35 mega years after the start of the solar system. It's actually consistent with some moon forming models that imply a nearly equal mass impactor and target in order to have significant mixing in the moon forming impact. So this way, the Pebble accretion model is actually consistent with the hafnium tungsten dating of the Earth, but we need a giant, a massive impactor. Okay, right. Let me go on for that and show you a little bit about what happens in the atmosphere of these models and what's a bit. I mean, people have obviously done magma ocean outgassing atmospheres before, but here we actually couple it directly to the planet formation model. So we let the atmosphere and the magma ocean interact, and also with the core while the planet is forming, and also up to 100 million years after its formation. Maybe we can start with Mars here. So here's my Mars analog. This is time. Accretion goes on for 5 million years, and then we run it for another 100 million years. Just want to, there's a lot of molecules here. Just focus on the interesting thing for Mars here is the hydrogen. This is the H2 here. It goes up. Actually, most of the magma ocean outgasses a ton of hydrogen. That hydrogen is then easily accelerated to escape speed by the radiation from the young sun. So you see, with time, the whole hydrogen atmosphere is like vanishing in like 50 million years. And along with it, it drags everything else. You see that it drags along with a lot of the water vapor. That's what we're seeing here, basically. That's the water vapor. It drags along with it a lot of the CO here and all of the CO2. So even if Mars starts with a massive atmosphere of CO2 as massive as Venus's, it actually all gets dragged away by the hydrogen. Then in the end, when it gets cold at the surface, when the whole atmosphere is gone, then the remaining water vapor becomes ice, and it forms an ice layer that's around between a 500 meters to 1,000 meters equivalent. And that actually is a lot similar to what we think is present on Mars today. So that was Mars. Obviously, the Earth needs more water than that, not just 1,000 meters. So if we do a model of Earth, there we assume that the Earth's mantle is a bit more oxidized than Mars. That's because Earth is more massive, and therefore there's a higher oxygen fugacity in the Earth mantle. And then most of the atmosphere is outgassed not as H2, but actually as water vapor. So we hardly have any H2 here at all, and therefore you cannot drive this massive mass loss. So the Earth is then actually gets water at the level of the Earth oceans, which is very good. And the Earth also gets a CO2 layer. So let's just look at the CO2, is the black one here. That's sort of similar to Venus's current CO2 content. So we think this is a good match to Earth and to Venus also because of this massive atmosphere. That for Earth will probably vanish later. The CO2 will get buried into the mantle again because of sedimentation, basically, whereas this didn't happen on Venus. Yeah. I want to sort of skip a little bit ahead and just want to skip this one maybe. I want to show you this one quickly, and that is basically that a lot of the results about the water content of Earth and Mars depend on the partitioning of water between the metal melt and the silicate melt. And actually, water has a preference to go into the metal melt and go into the core. So most of the water is actually sitting in the core of both our Mars and our Earth models. And we took some partition coefficients for water from Lee et al. 2020. So we took some value between 1 and 8, probably nominal values around 5. And if we then look at the surface reservoir of water on Earth and on Mars here for this value here, we see we get a nice 1,000-meter layer on Mars and a nice one Earth ocean on the Earth. And then you can see where is most of the water. It's in the core. There's a lot of water that's in the core in these models, and not so much in the mantle. Yeah. Let me skip to this one. I think this will be interesting to a number of people in the audience here. And that's what I call the nitrogen problem, because I think there has to be a way to distinguish between the classical terrestrial planet formation, where the Earth formed by giant impacts between of planetesimals, and then this Pebble Accretion. And I think it may be that it's the noble gases and the nitrogen which will determine this. So why nitrogen? Well, nitrogen is what we call siderophile. That's something that Greval will know a lot more about than I will actually. But it seems out that it's siderophile, meaning they would like to go into the core. Yeah. And the mystery here is, in a way, that if you look at Earth, that has sort of a few, here's the nitrogen over silicon ratio, but it has like a few ppm of nitrogen, and which is kind of equivalent to here. And you look at all the source material of Earth, it has much more nitrogen than the Earth has. And this is actually quite mysterious because it's not so easy to get rid of the nitrogen. So Earth has 1 to 3 ppm of it, and it's very similar to Venus's atmosphere. It's very hard to store in the core, and that's what some people would suggest. Maybe all the nitrogen is sitting in the core instead. But the issue is that it likes to go into the atmosphere. And that's sort of what I'm showing here. When we play around with different partition coefficients of nitrogen between metal and silicates, so kind of equal, and this 100 is very strongly going into the metal. Then we can see that the fraction of the nitrogen that in our model that is then in the atmosphere is sort of 100% for both these cases here. And then even if you use a value of 100, we can only get something like 50, 60, 70% stored in the core. That's what I'm showing you basically here. It's very hard to store nitrogen in the core. And the point then with nitrogen and noble gases is that most of their reservoirs are probably sitting in the atmosphere today. And this is an excellent opportunity to compare with the source material. And that's why I would say we have a problem with the traditional model of Earth formation, that we think it's formed out of these asteroids that we call chondrites. They have way too much nitrogen. They also have way too much noble gases, something that Matti has pointed out very clearly in his 2012 paper. But then back to the pebbles. Remember this plot here that I showed you earlier? I showed you how the water fits in with the Earth abundance, how the carbon sort of fits because there's sublimation of water and organic molecules in the envelope. We can do the same thing with nitrogen. Nitrogen, if it comes in with pebbles, with organics, is mainly sitting in the organics, and that also gets processed at high temperature and turns into various kind of very volatile species that don't make it to the surface then. So if we start with a value of 10 ppm of nitrogen, that's sort of what's in the ordinary chondrites, maybe. So we get pebbles that are like them. Then as we are accreting, we start with 10 ppm, and then with time, this nitrogen doesn't reach the surface anymore, and we nicely go down to a value of a few ppm here in the end. Yeah. So this way, I'm claiming that the low abundance of nitrogen and noble gases of Earth is actually a smoking gun, that the Earth did not form by traditional giant impact and planetesimal accretion, but by pebble accretion. Okay, I'm coming to my summary slide. I've talked about the streaming instability and showed you that the characteristic size of planetesimals formed by the streaming instability is 100 kilometers. Maybe there's a minimum planetesimal size. This is under investigation. The streaming instability produces predominantly prograde planetesimal binaries, agrees with what we observe in the Kuiper belt. Pebble accretion is an efficient mechanism to grow the cores of gas giant planets despite migration. And then I've shown you a new pebble accretion model for Earth formation that allows our planets to form exterior of the water ice line in the solar protoplanetary disk. Surprisingly, Earth formation in 3 to 5 megayears is completely consistent with hafnium tungsten dating of core formation of Earth if we have a massive moon forming impact. And finally, I've showed you quickly in the end that the volatile inventories of Venus, Earth, and Mars are completely inconsistent with chondrites as building blocks, but are actually consistent with pebble accretion and pebble snow as the main delivery of volatiles to terrestrial planets. And that was my last word, and I would like to thank you for your patience.
Thanks, Anders, for this amazing talk, and I'll be ready to take questions from the audience. So I'll narrate the questions that have been put up in the question and answers in this tab. And I think people, if they want to ask more questions, they can also raise their hands or add their questions in this tab. So the first question was by Neil Turner, and he has a thanks on this for a thought-provoking talk. If the terrestrial planets grew through pebble accretion, would the debris from the giant impacts have a composition different from the traditional picture? And how much such debris might be preserved in meteorites?
I mean, I don't know the answer to the latter part of the question. My view on the giant impact is that if the Earth forms here, and the Moon forms, and the Theia forms here, from the same drifting pebbles, then they're going to have the same composition in terms of isotopes. And I think that's also what we do see for the Earth and for the Moon. So I think it's completely natural in a way in the pebble accretion picture that the Moon and the Earth have the same composition, since the drifting pebbles are the composition. And I think anything coming out of that should have a similar composition also, from what I could see. So maybe you would have to find some kind of meteorite that was very Earth-like, maybe instantite meteorites or something.
Thanks. And there's a second question by Keelan Hodge, and it's are there atmospheric traces that can tell us pebble accretion was the formation mechanism, specifically talking about young, directly imaged massive planets with wide separation?
Yes, there is very much. One of the predictions of pebble accretion is that giant planets form far from the star, and that hot Jupiters are then scattered to become hot Jupiters afterwards. That clearly predicts that they should have a low water vapor content, since they form in a region of the disk where the water vapor was mainly in the icy form. So there's a clear prediction about the C2O ratios are going to be high, basically saying that they're going to be CO dominated when they accrete gas. So I think this is observed for many hot Jupiters also, although I understand that it's a very tricky business to measure the composition of hot Jupiters.
Okay, so then there's this next comment, a fairly long comment by Jeff Lucy. So he says, a comment on the formation of planetesimals. Streaming instability physics is fine, but it faces serious consistency problem between the small particle sizes and moderate turbulence intensities. Many recent studies find for protoplanetary nebulae. The initial conditions for Silicon
Streaming
streaming instability are not found given these combinations. So there may well be a need for an alternative way to create the first 100-kilometer size planetesimals, which can then perhaps grow by Pebble accretion in both the inner and outer nebula.
Yeah, I totally disagree with that. I know, Jeff, you're co-author of the Johansen paper, and I think it's very interesting to study the effect of turbulence on the streaming instability. But I have also argued many, many times that we have run countless simulations of the streaming instability with magnetorotational instability, with dead zone turbulence, with vertical shear instability. We always found the streaming instabilities to still survive. So it is an open question exactly what are the conditions for forming planetesimal by the streaming instability, but I don't agree that there's a killer argument against it.
Okay. So this next question by Anish Baburaj. This is, thanks for the talk. In the simulation results on slide 13, there is no Mercury.
Yeah, Mercury is a tricky one. I left Mercury alone because Mercury doesn't fit into my model, obviously. But I also think Mercury is a bit special. Mercury is very, very metal rich, as we know, much more metal rich than the other planets are. So I believe that Mercury formed in a different way. My favorite way is there must have been an evaporation front somewhere for metals and silicates and so on, and that somehow Mercury formed out of, probably, I would even say not by Pebble accretion, probably by accreting metal-rich planetesimals. But I'm working on a paper about Mercury, so hopefully I can give you an answer to that in a couple of years.
So Steve Dish, you can go ahead and ask the question.
Hi, yeah, thanks, Anders. Boy, you covered quite a lot of material. At the very beginning of your talk, which was great, by the way, you talked about the millimeter size aggregates of micron-sized particles as if those are the pebbles. But my understanding is that those would be Stokes number close to 10 to the -4, whereas streaming instability need closer to 10 to the -2 or 10 to the -1. So I advocated in the 2018 paper that turbulence is concentrating the millimeter size chondrules to aggregates, and that those are the feedstock for streaming instability. Is that consistent with what you said?
I think it is. I think it is. I mean, I think it's a little bit, it depends a little bit about when do you form the pebbles and when do you form the planetesimal. I think a Stokes number 10 to the -4 gets tricky. If you're down at 10 to the -3 or 10 to the -2, it certainly starts to become possible. So it's a little bit about, I mean, I think it's sort of an open end of the streaming instabilities. How small can you get, and to what degree do you need other effects to help you if you are smaller than that? And I could totally believe that there will be other effects coming in there also. But sort of, if you take a nominal chondrule size, it depends a little bit about the time also. If you would wait a few million years when the gas density would be lower, then it would also help. But yeah, I agree sort of that planetesimal formation from chondrule sizes is still sort of borderline understood. It's a little bit hard, yeah.
Yeah, I just want to point out in the 2018 paper, since we're predicting the turbulence parameter, we're predicting the density of the gas, we're predicting all these properties, we can predict what size turbulence would concentrate. And there is an incredibly good match between each chondrite class and the chondrule size in that class based on that.
Okay, I need to reread that then, yeah.
Thanks.
Okay. Then this next question by Raluca Rufu, and this is nice talk. Thank you. Can Pebble accretion create a distinct isotopic signature for Mars?
Yes, it can. So that's something I didn't talk about so much here, but the Mars seems to have a more inner solar system-like composition than Earth does. So Mars is more similar to the planetesimals that form very early on, like anchorites and uralites and so on. This seems to make sense that Mars is small. Hence, Mars actually grew by more planetesimal accretion. It accreted probably a lot of planetesimals that formed early. And we think that's why Mars is recording a fingerprint. Surprisingly, the Mars looks more inner solar system-like than the Earth does. But we think it's simply because it's smaller. Earth continued to grow and was then accreting more material that drifted in from the outer solar system, and therefore it has more composition between inner and outer solar system.
This next question by Devjit is, can giant impacts result in the loss of materials from the target? And if possible, can they be accommodated in the Pebble accretion model?
That's a good question. I actually don't know much about giant impacts. My impression is that it's hard to get rid of an atmosphere, but it could be that there's some hope there to get rid of some material and maybe get rid of some of the volatiles. If someone else is more expert on that, I don't know. Grevel, have you thought about this or about getting rid of the volatiles? Or?
About where?
Have you thought about getting rid of volatiles and giant impacts?
Yeah. So we have thought about these things. I'll talk to you later about those kind of things.
Okay, we can do that. I'll be curious to know more about that. Yeah.
And then this last question, Miriam says chondrite nitrogen is too high for Earth, but what about the achondrites as building blocks? Could that help explain the low abundances of nitrogen?
That's a super good question. That's something that I asked my cosmochemical colleagues at University of Copenhagen a lot about these days. Surprisingly, some achondrites don't fit at all. Actually, if you go and look at uralites and anchorites, they don't really seem to fit at all. They seem to have too many volatiles still. There are something like, now I'm really out on thin ice in my cosmochemistry. There's something called aubrites that are instatile-like, are Earth-like in their composition, and also are pretty poor in noble gases and nitrogen. But it may simply indicate that they come from another planetary body that underwent the same processes as the Earth. So there's some hope there, and I think this is a valid alternative path to pebbles. Yeah.
Okay, I think this final question, I think, Will, is Jupiter forming around 10 AU consistent with the observed wet-dry composition dichotomy in the asteroid belt?
Yeah, I'm not sure how much that has to do with it. My view on it, there was actually a paper by, I think, Andre Isidoro was on together with Sean Raymond, where there's a possibility the asteroid belt wasn't present to begin with, but it's sort of just what was scattered in by Jupiter migrating in, scattered wet planetesimals in, and then terrestrial planet formation or terrestrial planet migration scattered dry material out. So that I'm not entirely convinced that the dichotomy in the asteroid belt today is really what was there primordial. I don't think it has to do with an ice line in my view.
Okay. Thanks everyone for joining in for the talk, and thanks on this again for this amazing talk.